I wanted to record a couple of example problems for you before Tuesday's exam. So if you want to check them out, you can. And this would have been over what was on the last assignment on Fourier series stuff, and then also what would have been on what we did in class, but wasn't on any assignment yet with the Monte Carlo simulation stuff. So let's go through a few of these examples and make sure that we're all on the same page with everything. So let's look at the first one here, where I'm asking you to find a Fourier series for the function 2 minus x on 0 to 2 and x minus 2 from 2 to 4. That's representing, again, one period of the function, so we would that function would repeat over and over and over and over again. So let's use, again, GeoGebra to help, because I want you to do this on GeoGebra so that it will do the integrals for you and it will create the graph for you. Because on the exam, I want to see a screenshot of the answers for your integrals, and I want to see a screenshot for your final graph of what the function's supposed to look like. So remember, again, we need to figure out what the constant term is going to be for our Fourier series. I will handle dividing by the period and dividing by the half the period at the end. You're welcome to do it in the integral part too, but just remember which one gets divided by the entire period and which ones get divided by half the period, and I'll go through that here in a minute. So in this case, I've got a piecewise defined function. It's 2 minus x on the interval from 0 to 2. I will add the integral of x minus 2 from 2 to 4 for the second half of the interval, and we get 4. Remember, the constant term for your Fourier series gets divided by the entire period. In this case, the entire period is 4, so we will divide this 4 by 4 and get 1 for our constant at the end. To figure out our Fourier coefficients, remember we need to figure out the coefficients on the cosine pieces and the sine pieces. We typically denote the cosine pieces as a sub n and the sine pieces with the b sub n, those Fourier coefficients. So I'll define those as functions so I can refer back to them easily so that I can get a graph. So remember, to figure out our cosine coefficients, we're going to do the integral of the function over the entire interval and then multiply it by the cosine with the period changed appropriately. So we'll take our function 2 minus x, we'll multiply that by cosine of, I need nx, and then times something. Now remember, the coefficient that we need to multiply by is, if we call it b, remember that b, when we divide 2 pi by b, we have to get the period of the function that we're talking about. So what I mean by that is, when I do 2 pi divided by the coefficient I'm going to put inside of here, I have to get 4 in this instance because the period is 4. So the coefficient we'll have to use on the inside here will be pi over 2. Since everything here is multiplied together, the order doesn't matter. That's why I typed in the nx first and then typed in the constant that I needed so I could explain where the pi over 2 comes from. Again, now if we divide 2 pi by pi over 2, I'll get 4. I'll get the appropriate period. Okay. So we'll do that from 0 to 2. Let me move the graph a little bit so we can see. And then move the graph a little bit so I can see the whole thing. And then type in the integral of x minus 2, same cosine of nx pi over 2. And that'll be with respect to x. And I'm going to go from 2 to 4. In this one, I didn't bother telling it what the x variable was. I'm going to go back in and change that. Just make sure we have everything on the right numbers here. So here are our a coefficients, or a sub n coefficients. Okay. So again, took the function times cosine of nx, and then whatever this constant is what you need to use to adjust your period. We need the period to be 4. So I need to figure out 2 pi divided by what gives me 4. Solve that, I get pi over 2. Now, I don't want the graph of these a's. Notice that GeoGebra puts the graph in here. I don't want that graph. That's just noise for us as far as graphing purposes goes. I'm going to turn that off by just clicking on the little dot in that line. All right. Let's do the same thing for the b's. The syntax for the b's is identical, except that we're use sine rather than cosine. So integral of 2 minus x sine of nx pi over 2, And then again, the x goes from 0 to 2. And do the same thing for the x minus 2 piece. And it'll be sine of n times x times pi over 2. And then we'll do that from 2 to 4. Again, don't care about the graph or the b's. That's not helpful to us. So again, we'll turn off that little circle so that the graph doesn't appear. All right, so remember that the Fourier coefficients for the cosine and the sine pieces, these give us those, but remember again, I didn't put in the 1 over the period part. I still need to divide the a of n and the b of n by the period, the half the period, not the period. So the a of n and the b of n would both get multiplied by 1/2. The period is 4. Half the period then is 2, and I do divide by half the period, so I would divide by 2. But I can stick that out in front of the sum piece for when I create my function. So when we create our function to get the graph, I would do f of x colon equals, remember the constant was 1, I have to divide that 4 that we had back up there in line 1 by the entire period. Then I'll put a 1/2 out in front of my sum. I'm going to take a of n times cosine of n pi, or I'll write it the other way, nx pi over 2 plus b of n times sine of nx pi over 2. I need to create that sum for several terms just to see if we can get a graph. I'll do it from 1 to 10 so we won't bog down the website or the the computations. And then again, now this should give me my Fourier series. So we want a screenshot of the Fourier series part so we can see that. But also I want a screenshot of your graph. So if I scroll that over, you can see a screenshot of the graph. Now again, I would assume this would be on full screen on your computer. I did it on half screen so I could have the problems that I want to do with you over on the left-hand side. But that's how you would create a Fourier series in GeoGebra. Now, as a final final part of this, I would also want perhaps you to simplify what the series would look like if you were writing it down. And what I mean by that is, let's go up to these different coefficients that we have. Let's look at the sine coefficients first. So let's look at your b of n. Remember, the things that we're plugging in for n are integers here. Sine of n pi and sine of 2n pi will be 0 no matter what, so those would go away. Over here, cosine of 2n pi is always equal to 1, so that would be just a minus 4n pi here. I've got a plus 4n pi here, so those would go away. So it turns out that your b sub n terms here are always 0, so that wouldn't matter at all. So I don't even need to type those in over here. If I were to delete this part out in our Fourier series, I would get the same graph. So I don't even need the b's. On the a's, we can do a similar simplifying here. Sine of 2n pi is always 0, so this goes away. Cosine of 2n pi is always 1, so I could combine your 4 and 4 together to get 8. So on top, we would get 8 minus 8 cosine of n pi over n squared pi squared. And then also remember that your cosine of n pi is just negative 1 to the n. So if I were to write down a final Fourier series for this particular function, let me just flip over to something where you can actually see me typing some math. I would write f of x is equal to 1, that was our constant, and then 1/2 the sum n equals 1 to infinity. And then the a of n coefficients would be 8 plus 8 times negative 1 to the n plus 1, and then over n squared pi squared. And then we would multiply that by cosine of n pi x over 2. And that would be what I would want you to write for your final Fourier series. Not going to be doing any identities, but in some of them, if you've got things that have cosines of n pi's, cosines of 2n pi's, sine of n pi, sine of 2n pi, you should be able to simplify those. You should know which ones are 0, which ones are 1, which ones are alternating, those kinds of things. So being able to simplify that last little bit would be something I would expect you to be able to do. All right, so that was a Fourier series example, and we've done several Fourier series. You've got the answer key for the homework that we just did for the Fourier series as well. So, so let's go on and talk about some Monte Carlo simulation ones so that we're all on the same page with those. So let's look at number 2 here. We've got an iterated integral representing a triple integral. So in this case, we can think about dividing up our x's from -1 to 1, our y's from 3 to 6, our z's from 0 to 2. So I would want random values for each of those in this case. So I'm going to go ahead and label my columns to say which ones are my x values, which ones are my y values, which ones are my z values. Notice my limits for my x here are between -1 and 1. So for this first column, I want to do a random array. Let's use 5,000 points. Doesn't really matter. We'll do one column. The minimum is -1. The maximum is 1. So remember, again, that's our syntax for being able to create 5,000 random variables with the smallest possible being -1, the largest possible being 1. The commands for the next two columns are the same. We're just going to change the interval that we're worried about. Let's create 5,000 y values between 3 and 6. And let's calculate 5,000 z values between 0 and 2. All right, so basically what we've done here is we've calculated random points in the box defined by those three intervals. So the box in three-dimensional space that would be defined by those three intervals, we've picked random points in those boxes. Basically, we've created 5,000 boxes. We've divided that region, or that whole box, if you will, into 5,000 sub-pieces. Each one contains a point. Okay? So we're going to take each of these values, plug them into our integrand, and then multiply by the dx, dy, dz approximation. Well, remember, the sub-box will have approximately the volume of whatever the volume of the total box is divided by 5,000, because again, we took the total box and divided it by 5,000 pieces. So first, let's just calculate the function values for each of these. So this is y times x squared. Y is in B1, y is in B2, x is in A2. So we'll have B2 times A2 squared. The next one, we've got z times natural log of y. So I've got C2 times natural log of B2, and then plus, we've got the exponential function evaluated at A2. Remember, exponential function again is exp. So all we've done here is just plug the point into the function. We can copy this down all the way down easily by hitting copy on D2, hit Control, Shift, End. It'll take you to the bottom of the list, and then hit enter. All right, we want to add all of these up and then multiply it by our approximation for our delta x piece. So we'll use the sum command. The 5,000 points, since I've shifted everything down a row, the 5,000 points will be between D2 and D5001. We'll multiply that by, again, our approximation for delta x times delta y times delta z, our approximation for dx, dy, dz. Remember, that's going to be the volume of the entire box divided by the 5,000 points, or how many ever points you're using. In this case, 2 times 3 times 2 is 12. So we would do 12 over 5,000 for our approximation for the dx, dy, dz piece and get about 50.35. In the email I sent you, which I'm just pulling up right there, I said that I got approximately 50.2. This is for one simulation. If you rerun your simulation, of course, you'll probably get different values. Remember, again, the trick that I told you that if you want to run simulations over and over again, I can just hit Control-C on some empty cell, and then just hit Control-V several times. Notice I'm getting all sorts of values around all sorts of different things. If you actually wanted to see, say, 10 values all at the same time, let me show you one more trick that we can do. Let's hit Control-C to copy the actual value here. Let's move off to a different cell. But rather than hitting paste, rather than hitting Control-V, let's right-click on an empty cell. And then in paste options here, the second one will paste values. So rather than pasting the function that's in the cell over to a different cell, it'll literally take the value that's in that cell and paste the value. Now notice, it pasted the old value that we had, and then it's recalculated again. So if I scroll down one cell, and rather than hitting paste or anything else in the cell, hit Control-Y. Control-Y is redo. So in this case, what we want to redo is paste the values. So hit Control-Y, I get a new value. Scroll down, hit Control-Y, I get a new value. And again, and again, and again, and again, and again, and again, and again. Notice now I've made 10 simulations pretty quickly, all different values. And again, each time, all I'm doing is hitting Control-Y to paste the value that's in there. Okay. In this case, if you wanted to get an average, I can highlight these things at the bottom of your screen. There should be a default in your Excel probably down here that already has the average in there, so you don't actually have to calculate it. If you wanted to calculate the average, you can use the average command to average those cells. In this case, we did 10 simulations and got an average of about 50, 49.95. So again, that shows you how to do 10 simulations real quick and just grab the values out. We'll do this 3 more times. So hopefully when we do this the 3 more times, you'll get the hang of what's going on. All right. Let's go to the next one. The next one, we have the x's go between root y and 1 plus y. The y's go from 2 to 3. All right, so again, if I want to generate some x's and generate some y's, let's do the y's first, because again, the y's definitely go from 2 to 3. So let's do our random array, 5,000 points. Again, that 5,000 is kind of arbitrary. You can do as many points or as few points as you'd like. The smallest value is 2, the biggest value is 3. All right, let's do the x's now. Now, even though it looks like the region, well, it doesn't look like, the region is defined by curves here rather than values, I can still figure out what the smallest possible x is that we could ever have and what the biggest possible x is that we could ever have. So notice that our lower curve bound is x equals root y. Well, the lowest that y can ever be is 2, so the smallest that x could ever be is root y. Or root of 2, I'm sorry. The root of the smallest thing that we could have. One thing else you should check here, these things don't cross. Root y is always less than 1 plus y in the interval from 2 to 3, so we don't have any issues there with them crossing and have to do something weird. All right, so the smallest it could ever get is square root of 2. The largest it could ever get would be when if I plugged 3 into the upper limit here, 1 plus 3 is 4, so the biggest the x could ever get is 4. So when I do my random array here of 5,000 x values, the smallest it could be is square root of 2, and the largest it can be is 4. So again, I got those by plugging in the lower limit for y into the lower limit for x, and the upper limit for y into the upper limit for x. Now I've got my points. All right, So now we need to be a little bit careful because not all of these points do we want to plug into the function, right? I don't want to plug all of these x's and y's that we just generated in here. I only want to plug in the x's and y's that actually satisfy this definition of the region, that actually are in the region. If they're not into the region, then I want to assign a value of 0 to them. So the first thing we're going to check is whether or not the x value that we have is in between those two y values. So I'll use the if command. I need to make sure it's in between those two things, so I also have to use the and command because it needs to satisfy both of those at the same time. If my x coordinate is greater than or equal to the square root of the y coordinate, separated with a comma, and the x coordinate is less than or equal to 1 plus the y coordinate, then we want to use the point, otherwise we don't. So we'll use a 1 for the true, 1 for if true, if both conditions are met, and 0 otherwise. Again, copy that all the way down, so I'll hit copy on the cell, hit Control-Shift-End to get all the way down. So now that's giving me a test of whether or not the point is in there. If the point is in the region, then I want to use the function value. So if that C2 is equal to 1, then I want to take the point and plug it into the function. So I want to take A2 squared times B2. I'm just going to type rather than clicking. And then I want A2 times B2 squared. If my point's not in the region, then I by default use a function value of 0 because I don't want to count that as any, if you think about it as volume under surface again, I don't want to count that as any volume. So if the point's in the region, then plug the point in, otherwise use 0. Copy and paste all the way down again, just like we have before. Let's now add all of these up. So I'll sum this from D2 to D5001. Oops. And then I still need to multiply this by our dx dy approximation. Now, the way we've treated this, we've chosen points in the rectangle that goes from square root of 2 to 4 for the x's and 2 to 3 for the y's. So when I do my estimate for my dx dy, that's what I'm going to use. I'm going to multiply this by 4 minus square root of 2. That's my x interval. My y interval is 1, so I don't need to multiply it by anymore. So 4 minus square root of 2 is the rectangle that we used to pick all of these points. That's the area of that rectangle, and I'll divide it by 5,000 to get us our dx dy approximation. And now we notice we get 65.5, which is close to what we had for that 11C value that I gave you in the email that I sent to you before. But let's run some more simulations. So remember again, if I want to do 10 simulations, say I'll hit Control-C on the value. I'll move over to an empty cell, right-click, and I want to paste values. Oops. And then I'll just go below it, and I'll hit Control-Y. It'll paste again. Control-Y, paste again. I can do that 10 times. And then if I highlight it at the bottom of the screen, this says about 66.3-ish. 66.26 is the average. And again, if you're doing simulations, you might get values that are smaller, values that are bigger. We're just getting an estimate of the probability, or excuse me, not the probability, an estimate of the area, the integral here, in this case the double integral, using this iterated integral. Okay. So again, that's just a quick way that we can do 10 simulations. All right, let's do the next one. We're going to use this kind of bounding rectangle again idea to do the next two. All right, what we did here was first we just did a bounding rectangle here and then checked whether or not those points were actually in the bounding rectangle before we plugged it into the function. Okay? So we'll use a similar concept here, but what we're going to do here is we're basically going to calculate a percentage of points that lie in between two things, or lie inside of a region, if you will. So this one's inside the circle and has the absolute value of y being less than or equal to e to the x. So again, we need to generate some x's and y's. In this case, notice that we definitely want the point to be in the circle. Okay? So what we want to do in this case is think about a bounding rectangle around that circle. If we think about a bounding rectangle around that circle, the best that our x's, or excuse me, not the best, but the intervals that our x's and y's both have to lie in between definitely have to be between -2 and 2. So in this case, I might as well just go ahead and generate both columns at the same time. So I'll change the number here from a 1 to a 2, so I'll generate the x's and y's at the exact same time. And we'll make that from -2 to 2 for our min and our max. So now I've got a bunch of points in the rectangle, -2 to 2 for the x's and -2 to 2 for the y's. All right, what we want to calculate now is a percentage of the 5,000 points we just generated that are in the circle and have an absolute value of the y being less than or equal to e to the x value. Okay. So we'll use the if command again, and again we want to make sure both of those characteristics are met. So if a2 squared plus b2 squared is less than or equal to 4, and the absolute value of the b2, the y coordinate, is less than or equal to e to the x coordinate, so exp of a1. So I need both of those conditions to be met, which is why I'm using the AND command. If the point is in the circle and the absolute value of the y coordinate is less than or equal to e to the x coordinate, that's a good point, otherwise it's a bad point. So I'll use, if it's true, I'll use a 1. If it's not true, I'll use a 0. Notice I've got this value error here. It's because I typed A1 instead of A2 in for my EXP, which is trying to take EXP of a letter, which it doesn't understand. I wanted a number there, so I needed to change it to A2. My apologies for that. So let's copy this and paste it all the way down. So again, the idea here is to figure out a percentage of the points that meet these criteria. So we'll add up, or we can use a countif command, but since I'm using 1s and 0s, I can also use a sum. I'll just add up the C2 to C5000, 1. So of the 5,000 points we generated, 2,300 of them-ish are in the rectangle. So the percentage would then be the D2 divided by the 5,000, or how many ever points you use to generate it. That's the percentage of points that lie in the region. We'll multiply that by the total area of the rectangle. The area of the rectangle in this case is 16. It's a 4 by 4 rectangle, -2 to 2. So we get approximately 7.27 for that one, which is pretty close to the answer that I sent you in email. Again, if I want to do 10 simulations, I'll hit copy, right-click on an empty cell, paste values, scroll down, Control-Y, scroll down, Control-Y. Just hitting Control-Y over and over again. And then if I highlight, there's 10, and we got about 7.27, 7.28 for our answer. All right, last one, done very similarly. Here, though, we have an ellipse that it has to be inside, and then if it meets the second criterion, notice if I put that 4x squared plus 9y squared less than or equal to 36 in standard form by dividing both sides by 36, you get x squared over 9 for your first term and y squared over 4 for your second. Since we would have x squared over 9 in the first term, that tells me that my x's go between -3 and 3. Remember, it's the square root of that number that's in the denominator. So 5,000, 1, -3, 3 for my x's. For the y's, when we divide by 36, we'd have y squared over 4. Square root of 4 is 2. So your y's can range between -2 and 2. And now this is going to proceed just like what we did in the previous one. I need to make sure that both conditions are met, that the point is in the ellipse and this other inequality is met. So I want to make sure that 4 times a2 squared plus 9 times b2 squared is less than or equal to 36. That makes the point in the ellipse. And we want to make sure that a1 squared plus 4 times a1 plus b1 cubed, not 1, I did that in the previous one, a2 squared plus 4 times a2 plus a2 cubed is less than or equal to 7. Okay. All we're doing with this line is making sure that the point is inside the ellipse and meets the other criterion too. If they both are true, it'll give you a 1. Otherwise, we want a 0, just like what we did in the previous example. Again, we can copy this down, just like we have every other problem we've ever done with these. Copy it down all the way down. I want to add all of these up again, just like I did a minute ago. So add up the C2 to C5001. So of the 5,000 points we created, 2,800-ish satisfy both conditions. They lie in the region that we're interested in. So as a percentage, I'll take that 2,818, divide it by 5,000. And then I'm going to multiply it by the area of the rectangle that I used. Your x's went from -3 to 3, that has length 6. Your y's went from -2 to 2, that has length 4. 6 times 4 is 24. And we get about 13.7. Again, I can create a simulation, copy, paste special values, and then hit Control Y. That gives me 10 simulations. And again here, if I highlight, I get about 13.6 for the average. And again, if your Excel doesn't put this down at the bottom here where you can see the average, use your average command. You know how to use the average command to take the average of those particular cells. So anyway, hopefully these videos help you out here to do some simulations, and then another Fourier series example. Let me go show you what this region actually looks like over in GeoGebra. So if we graph, let me just reload, and we'll switch over to an algebra window. Maybe we'll switch to an algebra window and turn off the CAS. So if I type in 4x squared plus 9y squared is less than or equal to 36, we get the ellipse there. I'm not sure that GeoGebra will do the implicit inequality, but it'll do the implicit equation without any issues. If I do x squared plus 4x plus y cubed is less than or equal to 7. It doesn't like that, but if I put an equals 7, it does put the graph in there. And what we're looking at is this region in here. What we just calculated was using that Monte Carlo simulation was giving us an approximation for this region of the ellipse that's down below the curve. So you can at least get an idea of the area that we were looking for. So anyway, like I said, hopefully this will help as you're preparing for the exam on Tuesday.